What if I told you that 8 minutes ago, a machine on top of a mountain saw something no human eye, no phone camera, and no other telescope on Earth has ever managed to see? Something is different tonight, and by the end of this video, you will understand exactly why scientists are calling this the start of a completely new era in astronomy. Before we go any further, do me one small favor. Tap that like button right now, not because I asked nicely, but because this channel only grows when people like you decide a story is worth sharing. Hit subscribe if you want to be one of the first to know when something like this happens again. Now let's get into it. High up in the Chilean Andes, on a mountain called Cerro Pachón, sits a structure that looks almost too simple to matter. From the outside, it looks like a big metal box on a hill, but inside that box is one of the most powerful scientific instruments ever built by human beings. It is called the Vera C Rubin Observatory, and the location was not picked by accident. This spot is one of the driest, darkest, and clearest places on the entire planet. No city lights leaking into the sky, no thick clouds blocking the view, no moisture in the air to blur out distant starlight. Astronomers spent years studying weather patterns and light pollution maps before choosing this exact mountain. Because if you want to see the universe clearly, you need a place where the sky itself gets out of your way. Now let's talk about what makes this observatory different from every other telescope that came before it. Its main mirror stretches 8.4 meters across, roughly the length of a tennis court. That alone would be impressive on its own. But the real star of the show is not the mirror. It is the camera attached to it. This is the largest digital camera ever built for astronomy, capable of capturing images at 3,200 megapixels. Try to picture that next to your own phone, which probably shoots somewhere between 12 and 50 megapixels. This single camera captures roughly 100 times more detail than the phone sitting in your pocket right now. If you wanted to print out just one full photo from this camera at its true resolution, you would need hundreds of large television screens lined up in a row just to display it properly. Here's the part that really separates this observatory from everything that came before. Most telescopes take their time. They point at one object, gather light slowly, sometimes for hours, and produce a single careful image. This machine does not work that way. It captures a brand new, richly detailed image of the sky roughly every 40 seconds. Then it swings to the next patch of sky and does it again, all night, every clear night. Roughly 1,000 images captured before sunrise, and it plans to keep doing this for 10 straight years without stopping. Ask yourself why anyone would design something to run for an entire decade without pause. The answer is the real reason this observatory exists in the first place. It is not here to take pretty pictures for a few months and move on. It is running a project called the Legacy Survey of Space and Time. Instead of photographing the universe once, this machine is scanning the entire southern sky again and again, roughly every 3 days, in different wavelengths of light for 10 uninterrupted years. When you stitch all of those repeated images together, you do not just end up with a picture of space, you end up with something closer to a movie. A real continuous record of the night sky changing, built entirely from actual light, not simulations, not artwork, not guesswork. Scientists working on the project have described it as the greatest cosmic movie ever filmed, and that movie began rolling on June 30th, 2026. But before we go further into what this telescope has already found, you need to understand who it is named after, because her story is the emotional core of everything happening on that mountain right now. This observatory carries the name of Vera Rubin, an American astronomer who, decades ago, noticed something that should not have been possible. She was studying how galaxies spin, watching stars move around the center, the same way planets orbit a sun. Based on the visible matter alone, stars near the outer edge of a galaxy should move noticeably slower than stars closer to the center. That is simply how gravity works, when you can only count what you can see. Except that is not what Rubin found. The stars far out on the edges of these galaxies were spinning almost as fast as the ones near the middle. Something invisible had to be out there, adding extra gravity, holding these galaxies together in a way visible matter alone could never explain. Her careful measurements became some of the strongest evidence scientists had ever gathered for what we now call dark matter, a substance that gives off no light, cannot be seen directly through any telescope, and yet appears to make up a massive share of everything in the universe. Vera Rubin spent her career trusting the numbers, even when the numbers pointed towards something nobody could see. So when engineers finished building the most advanced sky survey telescope in history, naming it after her was not just an honor. It was a continuation of her own unfinished search. The camera itself deserves a moment of its own credit, because building it was its own enormous challenge. It was constructed by scientists and engineers at the Department of Energy's SLAC National Accelerator Laboratory, working with partners from research institutions around the world. The camera is roughly the size of a small car and weighs around 3,000 kilograms, yet it has to operate with such extreme precision that even the tiniest vibration could ruin an image. Inside sit 6 massive optical filters, each one tuned to capture a different band of light, from ultraviolet all the way through to near infrared. That range lets scientists study everything from young, hot, newly formed stars to faint, ancient, distant galaxies, all within a single coordinated survey. Every single image has to pass through layers of calibration before it even counts as usable data, checking focus, checking exposure, checking alignment down to fractions of a pixel. That is why the testing phase took years. A small mistake at this stage could quietly damage 10 years of future observations, and nobody involved in this project was willing to take that risk. Think about what that kind of precision actually demands from a team of human beings. Every mirror had to be polished to a level so exact that the smallest imperfection would blur light, traveling billions of years to reach it. Every wire, every sensor, every piece of software had to be tested not once, but over and over, because a single flaw discovered 5 years into a 10-year mission could quietly poison an entire decade of results. This is not the kind of project you rush. It is the kind of project you build slowly, check obsessively, and only release into the world once you are absolutely certain it will not fail the moment real science depends on it. If you are enjoying learning how this machine actually works, do something for me. Leave one word in the comments right now describing how you would feel looking up at a real live feed from this telescope. I want to see what word you pick before we go further into what it has already discovered, because the story is only getting bigger from here. All of that raw data does not just sit quietly on a hard drive somewhere in Chile. It travels straight to a data facility in the United States, hosted at the same SLAC laboratory that built the camera, where it becomes available to scientists across the globe. One of the major research groups working with this information is called the Dark Energy Science Collaboration, a team of researchers spread across different countries, all using Rubin's observations to measure the fundamental properties of our universe with a level of precision that simply was not possible before. What makes this project genuinely different from almost everything that came before it is how open the data will be. This is expected to be the first time this much astronomical data becomes available to this many people at once, opening the door for researchers at smaller institutions, students, and eventually even members of the public to explore real cosmic data that used to belong only to a small handful of professional astronomers with access to the world's biggest instruments. Now let's walk through what has actually happened so far, using real dates because the timeline itself tells an incredible story. On June 23, 2025, in Washington, D.C., the team behind this observatory held a public event called First Look, the moment the world finally got to see real images captured by this telescope. They did not disappoint. One of the very first images released was a glowing composite of 2 nebulae, giant clouds of gas and dust deep in space, known as the Trifid Nebula and the Lagoon Nebula. Other telescopes had photographed these clouds many times before, but never with this much detail. That single image was built from roughly 678 separate exposures, gathered across about 7 hours of observation time, and contained close to 2 trillion pixels of information. 2 trillion inside one glowing photograph of colorful cosmic clouds, detailed enough to zoom in endlessly and still keep discovering new stars hidden inside dust that older telescopes simply could not resolve. Another image released that same day captured a section of the Virgo cluster, an enormous collection of galaxies. In a single frame, you can see countless galaxies scattered quietly across the background, spirals and ellipticals glowing behind bright, foreground stars from our own Milky Way. Scientists expect that over the next 10 years, this survey will help catalog roughly 20 billion new galaxies. 20 billion galaxies currently sitting out there in the dark with no record of their existence at all, simply waiting to be captured. But here's what genuinely stunned the scientists who built this thing. In just over 10 hours of early test observations, before the real survey had even officially started, the telescope had already captured millions of galaxies and Milky Way stars and had already spotted thousands of asteroids inside our own solar system. 10 hours. Most observatories take years to build a catalog anywhere near that size. This one did it in less than half a day of testing. After First Look, the team moved straight into a long commissioning phase, fine-tuning every part of the system, testing the optics, the camera, and the data pipelines, making sure everything worked exactly as intended before the real 10-year survey could officially begin. During this testing window, something remarkable happened. In about 6 weeks, using nothing but early test data, astronomers working with this observatory discovered more than 11,000 brand new asteroids that had never been recorded before. 11,000 in 6 weeks. That stands as one of the largest single batches of new asteroid discoveries ever submitted to the International Astronomical Union's Minor Planet Center, the official worldwide authority responsible for verifying and cataloging small objects across our solar system. Inside that group of new discoveries, scientists identified 33 near-Earth objects, asteroids, whose orbits bring them relatively close to our planet. None of these newly found objects pose any danger right now, but tracking near-Earth objects remains one of the most important jobs any observatory can perform, because the more we understand about them today, the better prepared we are for anything the future might bring. On top of that, the early data also revealed 380 new trans-Neptunian objects, icy bodies orbiting far beyond Neptune, out where sunlight takes hours just to arrive. 2 of these newly discovered objects travel on such stretched, elongated orbits that at their farthest point they sit nearly 1,000 astronomical units from the Sun. 1 astronomical unit is the distance between Earth and the Sun, so these 2 objects travel almost 1,000 times farther from the Sun than we do. That is remote, frozen, barely explored territory. Researchers believe studying orbits like these could eventually help confirm or rule out the long-debated idea of a hidden 9th planet, sometimes called Planet 9, a world potentially 5 to 10 times more massive than Earth, possibly warping the paths of distant outer solar system objects through its gravity alone. Even if this telescope never spots that planet directly, finding more objects with strange, warped orbits gives scientists an important clue pointing toward whether it truly exists. That same early batch of data also let scientists refine the orbits of more than 80,000 asteroids that were already known but not fully understood. With frequent, detailed observations, astronomers sharpened those calculations, making our entire map of the solar system more accurate than it has ever been in human history. Then, in January 2026, something else caught the attention of the entire astronomy community. Using data gathered during the first look period, scientists published the very first peer-reviewed scientific paper based on observations from this camera. What they found was genuinely record-breaking. Hidden inside the data was the fastest spinning asteroid larger than 500 meters, wide ever recorded, sitting quietly in the main asteroid belt. Researchers said an object like this could not have been detected without the unique speed and sensitivity built into this camera. A deputy head of the project explained that finding thousands of new asteroids in such a short window and learning this much detail about them is only a small preview of what the full 10-year survey is going to uncover. Stop and consider what this really means for the future of the field. For most of human history, astronomy meant one person, one telescope, pointed at one tiny patch of sky, hoping something interesting happened to be there. This observatory flips that entire idea on its head. Instead of hoping to catch something rare, it simply watches everything, all the time, and lets the universe reveal itself on its own schedule. Objects that would have gone completely unnoticed for decades are now showing up in the data within days of forming or shifting or exploding. That shift alone, from occasional glimpses to constant observation, is arguably as important as any single discovery this telescope will ever make. This is exactly why what happened 8 minutes ago matters so much, and why I need you to stay with me for what comes next, because the story is about to get even bigger. If this kind of deep, honest space coverage is something you actually care about, then subscribing genuinely helps more than you might think. It tells this channel to keep making videos like this one instead of chasing shallow trends. So if you have made it this far, go ahead and subscribe now, because the next part of this story is where things get truly wild. On February 24th, 2026, this observatory issued 800,000 alerts to astronomers around the world in a single night. 800,000 separate events flagged in one night alone. New asteroids appearing, stars suddenly exploding as supernovae. Distant supermassive black holes flaring as they feed on surrounding material. Variable stars whose brightness rises and falls in patterns worth studying. Astronomers called this the true beginning of the alert stream, one of the final milestones standing between the observatory and the official launch of its 10-year mission. That mission officially began on June 30th, 2026, following years of construction, testing, and a careful operational review covering technical readiness, data quality, and calibration accuracy. From that night forward, this observatory began scanning the entire southern sky over and over, roughly every 3 days, collecting close to 10 terabytes of data every single night, with some estimates placing that number even higher once the survey reaches full operating speed. Across the full 10 years, the observatory is expected to generate roughly half an exabyte of information, an amount so enormous that entire teams of scientists and engineers spent years just building the software needed to sort through it. Scientists have said the amount of data gathered in the very first year alone will be greater than everything collected by every other optical observatory on Earth combined. Not close to it, greater than all of them put together. Once the survey reaches full capacity, this system is expected to send out as many as 7 million alerts every single night. 7 million. Each one representing a real change, happening somewhere out in the sky right now, an asteroid shifting position, a star exploding, a black hole flaring, a distant galaxy quietly changing in brightness. There is simply no way a team of human astronomers could manually review 7 million nightly alerts on their own, which is exactly why researchers built artificial intelligence systems specifically to filter through this flood of information in real time. The software sorts through the noise and flags the events that matter most, so scientists around the world can react within minutes and turn other telescopes toward whatever unusual event this observatory just detected. This approach is part of something scientists call multi-messenger astronomy, studying the universe using multiple types of signals working together, light, gravitational waves, and cosmic rays combined. When this observatory spots something like a possible collision between two extremely dense objects, or a sudden explosive event somewhere in deep space, it can immediately alert observatories around the globe to point their instruments at that exact spot, so the event can be studied from every possible angle before it fades away forever. Supernovae explain perfectly why this speed matters so much. A supernova happens when a massive star reaches the end of its life and explodes in a burst of light so powerful it can briefly outshine an entire galaxy. These explosions do not last long. They brighten quickly and then fade over days or weeks. If nobody's watching the right patch of sky at the right moment, the event simply gets missed forever. Older telescopes, moving slowly and covering small patches of sky one at a time, missed enormous numbers of these events for exactly that reason. This observatory solves that problem by never really looking away, because it revisits the same regions of the sky every 3 days without fail. Every sudden flare, every fading afterglow, gets caught somewhere inside that repeating cycle of images. The moment brightness changes in a pattern that matches a supernova, an alert goes out within minutes, giving astronomers around the world a real chance to study the explosion while it is still happening, not days later when the moment has already passed. One deputy director involved in running this observatory described the entire journey in a simple, honest way, explaining that it took 20 years of hard science, engineering, and sheer determination just to reach the point where the team could finally say action and start rolling on what he called this blockbuster movie of the universe. He also pointed out that millions of alerts generated in just the first couple of months of testing already proved this machine works exactly as intended. A genuine discovery engine, fully built and finally switched on. A planetary scientist at Caltech, who has followed this project since his earliest days in graduate school more than 2 decades ago, said, "Working with this data now feels like something he could only have dreamed about back then. Watching a project unfold over 20 patient years and finally become real, working, functioning science is not something many researchers get to experience in one career." He also pointed out something worth remembering. If you asked 50 different astronomers what excites them most about this telescope, you would probably get 50 completely different answers, because this single survey touches nearly every corner of modern astronomy at the exact same time, every single night. Over the coming 10 years, scientists expect this survey to reshape our understanding of our own solar system in a fundamental way. Researchers predict it could triple the total number of known asteroids and increase the number of identified trans-Neptunian objects by nearly 10 times what we currently know. Every single discovery adds another piece to the puzzle of how our solar system formed billions of years ago, how planets and smaller bodies settled into the orbits we see today, and what forces shape the outer edges of our cosmic neighborhood. But the deeper goal, the real reason this observatory carries Vera Rubin's name in the first place, reaches even further than asteroids and comets. Scientists are hoping this 10-year survey finally delivers real answers about dark matter and dark energy, the two biggest unsolved mysteries in modern physics. Dark matter appears to make up roughly a quarter of everything. Entire journey in a simple, honest way, explaining that it took 20 years of hard science, engineering, and sheer determination just to reach the point where the team could finally say action and start rolling on what he called this blockbuster movie of the universe. He also pointed out that millions of alerts generated in just scientists hope this observatory can finally help explain what dark matter and dark energy actually are, something no telescope in history has fully managed to answer. There is also something worth mentioning that rarely gets enough attention. Much of this data will not stay locked inside university labs or government facilities. Plans are already in motion to give students, teachers, and curious members of the public real access to explore parts of this catalog themselves. A teenager with a laptop in a small town somewhere in the world could, in theory, stumble across a genuinely new asteroid before any professional astronomer ever notices it, simply because the raw information is finally open. That kind of access used to belong only to a handful of institutions with billion-dollar budgets. Now it is being handed piece by piece to anyone curious enough to look. Think about everything this single machine is doing at once, right now, tonight. It is mapping our own solar system in more detail than ever recorded. It is discovering tens of thousands of new asteroids, some of which may one day matter for planetary defense. It is catching supernovae the moment they explode, giving scientists a front-row seat to some of the most violent events in the known universe. It is tracking supermassive black holes as they flicker and flare across billions of light-years of space. It is building toward a full catalog of an estimated 20 billion new galaxies. And underneath all of that, quietly, patiently, it is gathering exactly the kind of data that could finally crack open two of the biggest mysteries human science has ever attempted to solve, and we are still only in the earliest days of this 10-year mission. Everything described in this video, the 11,000 asteroids, the record-breaking spinning space rock, the 800,000 alerts sent out in a single night, the trillions of pixels packed inside one glowing image, all of it happened before the official survey had even fully begun. The real 10-year clock only started ticking on June 30th, 2026. Every single night from here forward, this telescope keeps watching, keeps scanning, keeps capturing data at a scale no observatory on this planet has ever managed before. And somewhere inside that endless flood of nightly images, hiding among millions of galaxies and thousands of newly discovered asteroids, there's a very real chance this observatory ends up capturing something completely unexpected, something nobody predicted, simply because it is watching the sky more closely, more often, and in more detail than any instrument in the history of astronomy. And maybe that is the part of this story that deserves to sit with you the longest. Vera Rubin spent her entire career staring at numbers that did not add up, trusting that something real was hiding behind them even when nobody could see it directly. She never got to see this observatory built. She never got to watch her name attached to a machine capable of scanning the entire sky every 3 days for 10 straight years. But in a strange way, every image this telescope captures is still an extension of the same question she spent her life asking. What is actually out there, beyond what we can see with our own eyes? Every alert, every newly discovered asteroid, every faint galaxy added to that growing catalog of 20 billion is one more small answer to a question one patient scientist refused to stop asking decades before any of us were watching. So here is where I leave you tonight. Somewhere above your head right now, whether you can see it or not, that telescope on a mountain in Chile is taking another picture and then another, 40 seconds apart, all night long, for years still to come. Every one of those pictures is a tiny piece of a puzzle that has been sitting unsolved for as long as humans have looked up and wondered what is really out there. We are not watching history from a distance anymore. We are watching it happen in real time, one image at a time, one alert at a time, one galaxy at a time. If this story pulled you in even a little, do not let it end here. Hit subscribe, ring the notification bell, and drop a comment telling me exactly which part of this story stuck with you the most. The trillion pixel nebula image, the fastest spinning asteroid ever recorded, the 800,000 alerts sent out in a single night, or the fact that this machine can send out millions of alerts every single night once it reaches full speed. I read every comment, and I genuinely want to know which fact made you pause and rewatch, because that tells me exactly what kind of story to bring you next. And if you learned something new today, send this video to someone who still thinks space exploration slowed down after the moon landing, because right now, in real time, we are living through one of the most productive periods in the entire history of astronomy, and that mountain in Chile sits right at the center of it. Thank you for staying with me until the very end. I will see you in the next one.